Hello and welcome to this video. In the previous video, we saw how we used gradient descent to minimize the cost function, that is this j of theta, and we saw what batch gradient descent was. So in batch gradient descent, what we did was during a single iteration, we go through the entire data set to calculate this error term before updating the parameters, that is theta naught, theta 1 and theta 2 in our case. If we consider only one feature from our data set, that is the living area, our cost function will look something like this. If we plot our cost function, it will look something like this. And initially, for random values of theta, let's assume the value of cost function lies here. And after the repeated iterations of the gradient descent, the cost function will be minimized and it will reach the global optimum of this function. But in a single iteration of this gradient descent, the algorithm has to go through the entire data set to update every parameter in a single iteration. So this type of gradient descent is expensive. To overcome this limitation, we have another type of gradient descent called as stochastic gradient descent. In this type of gradient descent, what we do is we go through all the training examples once, and for each training example we update the parameters. We can write it like this: we will go through every training example in the dataset and we will update the parameters theta naught, theta 1 and theta 2 simultaneously using this update rule for every training example, and we will keep an eye on the cost function and see if the cost function is minimized or not. In the stochastic gradient descent, we will go through the entire data set only once, but here in the batch gradient descent, for every iteration, we will go through the entire data set for every feature. So batch gradient descent, if the data set is big, is expensive. To overcome this, we have this stochastic gradient descent. This is the contour map of how batch gradient descent works. Initially, we have the value of j of theta here, and after every iteration, j of theta is minimized until we reach the global optimum. But in case of stochastic gradient descent, for every training example, we keep on updating the parameters. So in this case, the trajectory of the gradient descent will look something like this, because for every training example we'll keep on updating j of theta and it will look something like this until it reaches close to the global optimum. It may not reach the global optimum, but it will come closer to that. So that's it for this video. Thank you.